Chemistry. This is lesson 3 on periodic trends. So today we're going to learn more about the periodic table and how it's organized. So lithium has an atomic number of 3. The atomic number is called the Z number. The atomic number is the number of protons in the atom of an element. So here we take a look at lithium. That's the way it would appear on your periodic table. And you see it has 3 protons and 3 electrons. Previously, we said that similar charges repel and different charges attract to each other. These are referred to as Coulombic forces. So those repulsions and attractions of different particles are called Coulomb forces or Coulombic forces. Almost everything that happens in chemistry is the result of Coulomb forces. The core electrons are the electrons inside of the valence orbital. The core electrons are said to screen or shield the valence electrons from the pull of the protons in the nucleus. So if we take a look at the lithium atom, core electrons are all electrons inside the valence orbital. So lithium has 2 orbitals. The second one is the valence orbital, and that means any of the electrons that are not in the second orbital that are back in the first orbital are called core electrons. These electrons screen the valence electron from the protons, from the pull of the protons. So those are the core electrons, and the valence electrons are the ones in the outer orbital. Lithium just has 1 valence electron. So Z effective number, abbreviated, symbolized Z sub EFF, measures how much of the pull the protons and electrons feel. So if we look at our lithium atom, we see that there are 3 protons pulling on the electrons. But when you look at it from the standpoint of the valence electron, there are 2 electrons standing between it and the 3 protons in the nucleus. So they're effectively blocking the pull of the 3 protons, or some of the 3 protons in the nucleus. So the way you compute the Z effective number, that is how much of the pull of the protons that valence electron actually feels. You take the Z number, so that for lithium that's 3, and you subtract the number of core electrons. So for lithium that's 2. 2 of the electrons are inside of the valence orbital. So it's a simple equation, and when you do that, you have 3 minus 2 equals 1. So although lithium has 3 protons, its valence electron feels the effective pull of only 1 proton. So it's almost as though those 2 core electrons are canceling out 2 of the protons, and so what that outside electron effectively feels is just 1 proton pulling on it. Therefore, it's not being held as tightly to the atom as you might think. If you think that it has 3 protons, it effectively only has 1 proton that's holding it to the atom. Ionization energy is the amount of energy that is required to pull an electron away from its atom. So the man represents ionization energy. The ionization energy must have greater pull on the electron than protons do. So there you see the electron goes outside of the atom. If there's something putting enough energy, and that something is usually another atom that likes to pull on electrons, then that lithium atom in this case will lose that outer electron. Ionization energy is also called electron binding energy, but we use the term ionization energy. So ionization energy increases to the right and as you go up the periodic table. So the highest ionization energies, that means the atoms that it's the most difficult to pull electrons away from, they're the strongest, are in the upper right hand side of the periodic table. Ionization energy increases up a group, that's up a column, and right across a row in the periodic table. Ionization energy is greatest in the upper right-hand corner of the periodic table where helium is. So there's a perspective view of ionization energies of some of the elements on the periodic table, and you can see the upper right-hand corner has the highest ionization energies. So the lowest are in the bottom left, highest are in the upper right-hand corner. Now we're going to understand the reasons for this. Some are a little complicated, some are kind of simple. So ionizations are lowest when, 1, an electron is furthest away from the nucleus. That is, it's in an atom that has a lot of orbitals. And ionization energies are also lowest when the nucleus has fewer protons. So let's take a look at a couple of examples. We're going to look at lithium, which is on the left side of the second row. We're going to look at fluorine, which is on the right side of the second row. And we're going to look at bromine, which is in the fourth row. It's directly below fluorine. So lithium has a lower ionization energy for its valence electron than fluorine because its valence electron is the same distance from the nucleus as fluorine's electrons. In other words, they both have 2 orbitals. So the electrons in their valence orbital are all the same distance away. But lithium has only 3 protons to attract it, while fluorine has 9 to attract it. So what determines whether something has high ionization energy when you go from left to right across the periodic table is which one has the most protons. And fluorine definitely has more protons than lithium. So if we look at it from the standpoint of Z effective, that is, how many protons do the electrons feel pulling on them, we already did the calculation. Lithium has a Z effective number of 1. So the valence electron in lithium only feels the pull of 1 proton. Fluorine, if we do the same calculation, has a Z effective number of 7. So we can quickly do that calculation. Fluorine has 9 protons. If you subtract the core electrons, it also has 2, just like lithium. It has 2 electrons inside of its valence orbital. So that's 9 minus 2 is 7. So lithium's valence electrons, all 7 of them, feel the pull of 7 protons each, whereas lithium's 1 valence electron only feels the pull of 1 proton. Bromine, so that's down in the lower right corner, you see there. You see that's an atom that has a lot of orbitals. So bromine has a lower ionization energy for its valence electrons than fluorine because it has more orbitals. So its valence electrons are farther from the nucleus. Electrons farther from the nucleus have more energy, and it doesn't take as much energy for another atom to come in and pull one of those electrons away. So each electron in an atom has its own ionization energy. These are called first ionization energy for the first electron ionized, the second ionization energy for the second electron, and so forth. So the valence electron of lithium has the lowest ionization energy. It is the easiest to pull away because it is shielded from the nucleus and has a Z effective of 1. It also is in the second orbital, so it's farther away from the nucleus. So there you see it flies away. The first ionization energy of lithium is 520.2 kilojoules per mole. Now that's a new unit of measure that we haven't talked about yet. We will later, but it's a measure of energy, how much energy it takes to pull away an electron. Note that the units kilojoule per mole are a measure of energy we will discuss later. Each electron in an atom has its own ionization energy. These are called the first ionization energy for the first electron ionized, and the second ionization energy for the second electron, and so forth. So the second electron of lithium has a much higher ionization energy. It is not shielded from the nucleus, and it feels the pull of all 3 protons. So it has a Z effective number of 3. So it's much more difficult to pull the second electron away. So there it goes. It gets pulled away. So the second ionization energy of lithium is 7,298.1 kilojoules per mole. So it takes a whole lot more energy to pull that second electron away. The last electron of lithium has the highest ionization energy. It is not shielded from the nucleus and feels the pull of all three protons. In addition, it does not feel repelled by the other first orbital electron, which has been removed. So it has a Z effective of 3. That's the same as the other first orbital electron, but it doesn't feel any repulsion. It's not being pushed away by another electron. So it is the most difficult electron to remove from lithium. So ionization energies of electrons increase as you take away electrons. As you take away electrons, the electrons that remain have higher and higher ionization energies. The third ionization energy of lithium is 11,815, so it goes up significantly. Electronegativity is how much an atom wants to pull on an electron from an atom to which it is bonded, and we'll discuss that concept later. Electron affinity is how much an atom wants to pull an electron toward it from an outside atom, from outside of itself. Now, you will not understand the difference between these two definitions at this point, but just understand that we use the term electronegativity for both of these definitions throughout the class, so you will probably never hear the term electron affinity ever again. So there you see the little man is inside the atom. He's trying to pull in an outside electron. So electronegativity is how much an atom wants to pull an electron toward it, either from an outside atom or from an atom to which it is covalently bonded. And we'll discuss covalent bonds and bonding later. So the man represents electronegativity. So electronegativity wants to pull in an electron like that. Electronegativity is measured on a scale from 0 to 4 called the Pauling scale. Fluorine has the highest electronegativity at 4.0. So let's look at the trends in electronegativity across the periodic table. Electronegativity increases as you go up in a group and right in a period. So it's exactly the same pattern as ionization energy. So the upper right-hand corner, those atoms, that would be nitrogen, oxygen, fluorine, chlorine, have the highest electronegativities. That means they're the best at pulling in outside electrons. In the lower left-hand corner of the periodic table, and in fact the entire left side of the periodic table, those elements are very poor at pulling in outside electrons, and in fact they never do it. So notice that it's the same as ionization energy. So here you see also a perspective of electronegativity, a perspective view. So electronegativity is greatest in the upper right-hand corner of the periodic table where fluorine is. So the lowest electronegativities are there on the lower left. The highest electronegativities are on the upper right. The elements on the right side of the periodic table are called noble gases. Noble gases have no electronegativity, and we will learn the reason for this. So there you see, you notice that it looks like the entire periodic table there, except you don't see helium, neon, argon, krypton. They're not there. Why is that? Noble gases are not shown because they have no electronegativity. The reason is they have a full orbital. Each one of them has a full orbital. For fluorine, it's the second orbital. For chlorine, it's the third orbital. For bromine, it's the fourth orbital. Because they have full orbitals, they're happy. They're content with the number of electrons that they have, and they don't want to pull in any new electrons. So noble gases have no electronegativity. They have very high ionization energy. It's very difficult to take their electrons away from them, but they have no interest, no desire to pull in electrons from the outside. So let's examine why that is. Electronegativities are highest when an atom has fewer orbitals and electronegativities are highest when the nucleus has more protons. So the first one, fewer orbitals, deals with a column going from bottom up to top. And nucleus having more protons, number 2, has to do with going left to right on a row in the periodic table. So as you gain more protons going from left to right, the electronegativity is going to be higher. So it's pretty much exactly the same as ionization energy. So lithium has a lower electronegativity than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull in electrons as well as fluorine. So fluorine has 9 protons to reach out and pull in outside electrons. Lithium only has 3. And they both have the same number of orbitals. So fluorine does a much better job of pulling in outside protons than lithium. In fact, fluorine is the best on the periodic table at doing that. Has the highest electronegativity. Now let's look at a column. Let's look at the column with fluorine, chlorine, and bromine. So bromine has a lower electronegativity than fluorine because bromine has more orbitals and more core electrons. The electrons outside of the atom are screened more from the nucleus of bromine, so the atom can't pull in electrons as well as fluorine can. Atomic radius. Atomic radius is half the distance between the nuclei of 2 bonded atoms. It is roughly the distance from the nucleus of an atom to the valence electrons. If you think of math class and what the radius of a circle is, it's the distance from the center of the circle to the circle. And so you can think of that for an atomic radius. It's the distance from the nucleus to the outer orbital. That's not an exact definition, but it's close enough. Technically, it's the definition that I just read. It's half the distance between the nuclei of 2 bonded atoms, so it's roughly the distance from the nucleus of an atom to the valence electrons. Atomic radius is important because some chemical properties depend on whether an atom can fit into small spaces. So atomic radius decreases as you go up a group, and it decreases as you go right in a period. So the atomic radius is the smallest in the upper right-hand corner of the periodic table. That would be for helium, neon, fluorine, chlorine, some of those elements up there in the upper right. So let's examine why that is. Atomic radius are highest when an atom has more orbitals, so that's a pretty obvious one. If you start at fluorine and go down to chlorine and then to bromine, you keep adding orbitals, and they expand outward and outward and outward, and so the atom gets bigger as you add orbitals. So if you go down the periodic table, the atomic radius gets bigger. That one's kind of obvious. The one that's not so obvious is number 2. The nucleus has fewer protons. So lithium has a larger atomic radius than fluorine because it has the same number of orbitals but fewer protons. So lithium doesn't pull electrons as well as fluorine. When you think about that, that seems a little odd. A typical lithium atom has 3 protons, 3 electrons, and 4 neutrons. That's a total of 10 particles. A fluorine atom has 9 protons, 9 electrons, and 10 neutrons. That's a total of 28 particles. So fluorine has almost 3 times as many particles, pieces to it, as lithium, and yet it's much, much smaller. The reason is very similar to the reasons for ionization energy and electronegativity, and that is fluorine has more protons to pull on the outside electrons, and so it pulls them in tighter and tighter and tighter, and it makes for a very small atom. Lithium only has the 3 protons to pull on its electrons, and so it can't pull them in very well, so they tend to stay farther away from the nucleus, and therefore lithium is a larger atom. So fluorine in the upper right-hand corner has the smallest radius. Bromine, as we mentioned, has a larger atomic radius than fluorine because it has 4 orbitals compared to only 2 for fluorine. So there you see kind of an illustration on this of the relative sizes of different atoms. And you look on the second row, look how much bigger lithium on the upper right is than fluorine over on the right-hand side of the second row. Fluorine is not just a little bit smaller than lithium, it's much, much smaller than lithium because its protons pull the electrons in much tighter. The biggest radius are going to be on the left side and particularly down lower on the periodic table. The second period elements show that lithium is much larger than neon. Even neon is even smaller than fluorine. This is due to the fact that both lithium and neon have 2 orbitals. However, neon has 10 protons pulling on its second orbital, while lithium has only 3 protons pulling on its second orbital. So here's a summary of the periodic trends, and you should be aware of these. As we move to the upper right-hand side of the periodic table, ionization energy and electronegativity increase while the atomic radius decreases. Why? And the answer to all 3 of those has to do with the number of protons. As you move, if you stay in the same row, we'll just say the second row, as you move from left to right across the periodic table, you keep adding protons to each element. And so what that does is it makes it harder to pull the electrons away from the element with the most protons. That would be fluorine. It makes it easier. Fluorine is better at pulling in outside electrons because of the number of protons, and the atomic radius is smaller because the electrons that it has are pulled in tighter. And so comparing fluorine to lithium, ionization energy increases, electronegativity increases, and atomic radius decreases. As you go up the periodic table, the determining factor is the number of orbitals. So as you go up the periodic table from, say, bromine to fluorine, the ionization energy increases. That's because the electrons are closer to the nucleus. They're pulled in by the protons in the nucleus of fluorine better. Bromine, keep in mind, has a lot more protons than fluorine. So you might think, well, that ought to be very good at holding onto the electrons. But for elements in the same column, the same group, it's not the number of electrons that's important, it's how many orbitals. And because bromine has 4 orbitals, its outside electrons are very far away from the nucleus, and therefore they're easy to pull away. So that's low ionization energy. Fluorine has much higher ionization energy. Electronegativity, same thing. Bromine has a whole lot of electrons that its protons need to reach out through to grab an electron from the outside. And in fact, bromine rarely does that. Whereas fluorine doesn't have as many protons as bromine, but it only has 2 orbitals. So the electrons in fluorine can more easily reach out past the second orbital and grab an electron from the outside. So as you go to the upper right, the electronegativity and ionization energy increases. And finally, the atomic radius decreases from bromine to fluorine. This is the most obvious one because you have fewer orbitals. So you don't have electrons farther away from the nucleus. So memorize those trends. Okay, as you go across a period, that is a row, more protons are added to the nucleus. The electrons are pulled in with greater force. This means that atomic radius becomes smaller. The energy required to pull an electron out of that atom becomes greater. That's the ionization energy. And the ability of that atom to pull an electron in, that's electronegativity, from the outside becomes greater. That's as you go to the upper right-hand corner of the periodic table. As we go down the periodic table, more orbitals are added. This makes the atomic radius larger, and the outer electrons are farther away from the nucleus. This increased distance makes the ionization energy and electronegativity less. It's easier to pull an electron away from an atom that has a lot of orbitals because the electrons in the valence orbital are farther away. And it's a lot of electrons for the nucleus of that atom to reach out through and grab outside of electrons, so electronegativity is also less as you go down the periodic table. Okay, so each column of dots is a period or row on the periodic table. The yellow dots represent the second row, with the top right dot being lithium. So let's just look at what this table is telling us. It's telling us the atomic radius in something called picometers. That's 1/1 trillionth of a meter. It's really, really tiny. And as you go from left to right, it's getting you have bigger and bigger elements. In other words, you're going across and down the periodic table. So it tells you the atomic number. So the yellow dots represent the second row, with the top dot being lithium and the bottom dot being neon. The radius decreases across the periodic table for the reasons discussed earlier. So if you look at the yellow dots there, lithium's at the top, neon is at the bottom, and you can see that the atomic radius gets smaller as you go from lithium across from left to right on the periodic table to neon. So it gets smaller. Now, once you get to neon, the second row, you've got to add a third orbital to go to sodium, Na. So all of a sudden the radius jumps way up, and that's the red dots. So the very first one is sodium, Na, on the periodic table, and then you go across the periodic table all the way to argon, which is at the bottom of that column of red dots. Once you get to argon, you're at the end of the third row, so now you're going to have to add a fourth orbital, so that jumps way up, and that's the light blue dots. And that starts with potassium, K, on the periodic table. You'll notice there's more dots in the fourth row. That's because of the transition metals. You did not have transition metals in the first three rows, but that's that middle area that's kind of low down on the periodic table, and that's the transition metals. So you have 18 dots there. Same with the fifth and sixth rows. So the radius increases with each row because an orbital is added. The blue, brown, and green columns have 18 dots because there are 18 elements in these rows. And that takes care of this lesson on periodic trends. So these become important when you try to understand why some elements bond, why some elements don't bond. And chemical bonding is really, creating chemical substances is all about bonding and understanding that. Okay, so we'll learn more about bonding in later lessons. And we'll see you on the next lesson.